Please welcome now Eric Rignot, Chemistry Donald Bren Professor of Earth System Science and Department Chair, JPL, and Chancellor Professor of Earth System Science, UCI.
Thank you. Very glad to be here. Now I have the difficult task to follow the speech of Jerry. I'll do my best to entertain you. I'm going to talk about Greenland and Antarctica in a few seconds, but first I want to mention the motto of our Department of Earth System Science at UCI, which is Global Climate and Environmental Change, Causes, Impacts, and Solutions. We're looking at the causes of climate and environmental change, mostly from human-induced disturbance. We'll look at the impact on natural ecosystems, on marine life, but also on human systems. But more and more we think that we need to be a full part of the solutions as well. And the solutions goes well beyond what we do in the Department of Earth System Science. It means that we have to work together with engineers, social ecologists, educators, and there's not a structure in place in our campuses to do that. So I really think that down the line, of course, we have to educate our young, but we need to also create some Climate Institute structure focused on climate change and solutions that bring together all these forces. Greenland, Antarctica, lots of potential sea level rise locked up. 7 meters in Greenland, 57 meters in Antarctica. We like to think about the changes in mass of these ice sheets in gigatons, billion tons per year. And 1 billion ton of ice is the amount of water that a city like Los Angeles consumes every year. 360 gigaton raises sea level by 1 millimeter. In the past century, we raised sea level by 20 centimeters. Right now, we're on pace at 30 to 40 centimeters, and we are probably going to end the century at 1 meter per century sea level rise. But as a glaciologist, what worries me is that we can go much faster than that. We could go to several meters per century sea level rise. Now, we're all probably familiar with the concept that in a warmer climate, ice melts from the top and creates these rivers of superglacial ice in Greenland. So that's part of the story in Greenland. That's not part of the story in the Antarctic because it's not warm enough yet to melt Antarctica from the top. Antarctica looks white to the visible eye, but when you take radar images of the continent, you can see the flow of the ice from the interior of the continent all the way to the coastline through these channels that we call the ice streams and glaciers that transport all the mass from the continent to the ocean. And these rivers of ice are the key to the future of the ice sheets because they can change their flow in response to climate forcing in a very big way. Not just 10, 20%, 50%. They can triple their speed. In fact, in the Antarctic Peninsula, following the breakup of Larsen B, we saw some glaciers speed up by a factor 8. Right? And if you were to do this all around Antarctica and speed up all the glaciers by a factor 8, you would raise sea level 4 meters per century. So it's not a lullaby, it's something that could happen. Now, these glaciers end up in the ocean, and they break up into icebergs. Even the traditional books of glaciology tell you, ice melts from the top and then breaks up into icebergs. But what we discovered in the last 10, 20 years is that there's a lot going on below the waterline, below this big iceberg. This big iceberg, by the way, took about 15 minutes to break up. It's about 1 billion tons right there breaking up. Here's our water going to the sea. So glaciers end up in the ocean, salty water. Ice doesn't like salty water. That's why we put salt on our roads to melt the ice, right? The melting point is minus 2 degrees, and when you bring that water a kilometer down, it becomes minus 3 degrees. And in the polar regions, the warm water is found at depth, not at the surface like it is in California. So if you want to swim in the Antarctic, you have to swim deep. 400 meters, 700 meters, it's a little bit challenging, I recognize that. And that warm water around the Antarctic is in the Antarctic circumpolar current, that you see on the top right here. And it's changing. We know that that warm water is becoming more in contact with the Antarctic. What has this to do with us? Well, it has to do a lot with us. The strength of this current depends on the wind. The wind depends on the temperature difference between Antarctica and the rest of the world. And right now, the world is warming faster than Antarctica. There's no albedo feedback in Antarctica. It's as white as ever. The sea ice is not melting. And the ozone depletion has actually cooled the Antarctic stratosphere. So the temperature difference is getting bigger, the winds are getting stronger, and they tend to push the subsurface waters towards the Antarctic glaciers and melt them away. And this started around the 80s. Around the 80s is when the climate system clearly departed from the regime of natural variability. Same thing in the Arctic. The warm waters there come from the subtropics, from the Gulf Stream. It's bringing water around the glaciers and melting them away. But there the story is a bit complex, still a subject of debate, because the Arctic is warming 2 to 3 times faster than the rest of the world. And that's because the snowmelt on all the land we have in the northern hemisphere, they didn't put enough land in the southern hemisphere. They forgot that when they designed it. Is melting away. The sea ice is retreating very fast, as you know, so the land and the ocean are absorbing more solar radiation. So now the temperature differential in the Arctic is getting smaller, and as a result, the prevailing jet stream becomes less strong, weaker, and starts to wobble. And the wobble also tends to become stationary, fixed by topography. That's why you can have some cold snaps in Washington, D.C. that generate a bunch of tweets about climate warming, whereas in California, we're still going to the beach in our shorts, right? And in Greenland, there's big warm spells of warm air and warm ocean temperature that melt the glaciers. Now, there's a bug in the system. And that bug was pointed out way back in the 60s by a visionary scientist. If a glacier starts retreating on a retrograde slope, meaning the bed elevation gets deeper inland, it's unstable. And there's a lot of places like that because when you put a lot of ice on land, it depresses at the middle where it's thicker. And when people started to survey West Antarctica in the 60s and find out that the bed was getting deeper inland, they went like, how come we even have an ice sheet here? It should not be there. So the idea was kind of dismissed with time, but American scientists who work in Alaska and study the glaciers there, they knew very well that when a glacier retreats in deeper ground, it goes like crazy until it reaches higher ground. They knew that very well, so the concept is not new. Now, we know what's happening to the ice sheets today very well, right? Climate change is not about belief, it's about data, and we have lots of data, and we're getting more data. We can tell you what's happening to every glacier at any time in Greenland and Antarctica now. That was not true 20 years ago. And we have this mission called GRACE that is the equivalent of weighting the ice sheets on a monthly basis to tell us what's going on. And you see in this animation here, all the areas in red are areas that are losing mass very rapidly. So it's affecting all of Greenland, all corners of Greenland. In fact, the north, even more than the south. And in the Antarctic, it's affecting a few areas. Thank God, only a small places in the Antarctic. And you see the plots for Greenland on the left, Antarctic in the middle, and all of the world's and ice cap glaciers, which GRACE can sample like no other instrument can do. You see that these curves are going down, the mass is decreasing, and you see some curvature in these plots that show that the mass loss is increasing every year. It's increasing with time. It's getting worse. And if you extrapolate these results to the end of the century, we get about 80 centimeters of sea level rise. You add thermal expansion of the ocean, you get about a meter. We are on course for a meter sea level rise per century. Now, where are the bugs, right? I'm not so worried about the glaciers that are on high ground or going to be away from the ocean very soon. I'm worried about those with retrograde slope that are going to stay in contact with the warm ocean all the time they retreat. So in Greenland, there's about 3 floodgates. So we see a map of the bed here on the right. Everything in blue is below sea level. I have to use this thing here, see if it works. Oh, didn't work. Jakobshavn is way, 0.5 meter sea level rise. Then there's a northeast ice stream with Zachariastrom and Nordgalfjords Fjord, and Petermann and Humboldt. And one day, I bet you the kids in school will know the name of these glaciers. I labeled in red those for which we opened the floodgate already. So you see 2 red boxes in Greenland. And on Petermann and Humboldt on the top left, we have a regime of alert, which is shown in orange. Now, in the Antarctic, there's a lot of bugs. This place has been bugged all over. Right? We have one sector that's changing very rapidly. It's the Pine Island Thwaites sector, which is on West Antarctica, which is shown in red, and that's 1.2 meter sea level rise. And that will entrain the collapse of the rest of West Antarctica, and that's 3 meters of sea level rise. But we also see some warning signs in the East Antarctic. You see 2 orange blobs there. One is Totem, one glacier, 3.5 meters sea level rise equivalent. Thankfully, we found that this glacier will have to retreat over 50 kilometers of prograde slope before it goes into the deep stuff. So we have maybe a century to worry about Totem, maybe less. The one next to it, Denmark Glacier, I just talked about it at AGU earlier this week, is retreating about half a kilometer per year into a very deep trough that we didn't know about, and that deep trough goes 3.5 kilometers below sea level. And that glacier holds 1.5 meter sea level rise, as much as half of West Antarctic. So most of these changes are happening close to the warm water, and I'm going to take you here to the Pine Island Thwaites Glacier area with this animation showing the flow speed, the name of these glaciers, Pine Island, Thwaites. We find also a glacier named Pope, Smith, and Kohler, and I'm sure you will learn about these glaciers in the future. They're all responding to more warm water coming to melt them from below, and they're retreating very fast. So we're familiar with glaciers retreating in the Alps or in the Rockies, right? You can go on a hiking trail and see a sign that says the glacier used to be here 50 years ago, and you're going to walk a few kilometers to see where the glacier is, and you're going to go, wow, a lot of stuff disappeared. Well, in Greenland, they're retreating at half a kilometer per year. Right? So they're going to do the same thing in 10 years instead of a century. But in the Antarctic, Pine Island and Thwaites are retreating 1 kilometer per year, and the Smith Glacier is retreating at 3 kilometers per year. These numbers are mind-boggling. And if you look at the glacier from the top, you won't see a thing. Right? They're fading a few meters per year. Everything is happening at the bottom. 3 kilometers per year, it's kind of a ringing bell for our community, because there's a paper published a few years ago making very dire projection for the Antarctic, and some people thought it was a little bit extremist. In their model, the modelers said, we will not allow the glacier to retreat more than 3 kilometers per year. I'm not sure why, but we're seeing that already in the Antarctic, and we're not in a regime of total collapse of the ice sheets yet. So we haven't seen nothing yet, basically. 1 meter per century, so that's going to affect a lot of population around the world, obviously. But there's something even more worrisome down the line. The paleoclimate record showed that in the last interglacial, 125,000 years ago, when the temperature of the planet was a little bit warmer than today, or maybe just about the same, sea level was 6 to 9 meters higher. Right? We know that a bunch of Greenland was gone, and West Antarctica was gone, and some parts of East Antarctica to be identified was gone too. So what that means is that if we bring the climate system back into that regime, we are committing ourselves to something like this. And if I look at the picture of what's happening today around the ice sheets, the very same areas that reacted in the last interglacial are the ones that we're seeing changing today. So it's like, get a clue. Now, I work on sea level rise. There's a lot of other things that are affecting us, and not just climate change, but also environmental change. I think in California, we're very sensitive to wildfires because of forest dieback. The trees, the most evolved plant on the planet, are dying because of climate change, because of drought and parasites, and that creates wildfires, and wildfires kill people. And when we kill people, suddenly we start thinking climate change is a real thing we need to worry about, unfortunately. The loss of biodiversity is, as an academic, is something that worries me even more, because the loss of biodiversity is actually threatening the very essence of life. Loss of species. Geez, we are one species too. Right? Flooding, sea level rise, the biggest concern down the line is not how we're going to adapt to it and build levees and ask people to move. Some places people won't be able to move, so they're going to have to migrate to some other place, and that's going to create a lot of problems. That's going to create problems for everyone, not just the poor people affected by it, but where the poor people are going to go. So solutions. Right? There's some good news. The Stone Age didn't end because we ran out of stone. It's important to remember. So the age of fossil fuel will not end because we ran out of fossil fuel. We just need to find something else to burn, or maybe not burn, and create a sustainable environment. So we need to educate our kids about all these issues here that I put on the board that are important. Basic physics. They need to understand basic physics of climate change and how it's going to impact us. They need to understand the concept of climate stability. Climate stability is good. There's no reason in the world humanity wants a changing climate. We've had 10,000 years of stable climate that allowed the development of civilization. Sustainable development, environmental justice, as pointed out by Ram and others, the poor people are going to be affected the most, and that's not fair. We need to transition to carbon-free energy. The solutions are there today. It's just a scale problem and implementation problem. The solutions exist. We don't have to dream them up. But it's going to take more than that. I'm personally not satisfied with curbing our carbon emission. I'm not even satisfied with zero emission scenario. We're going to have to pay the price for what we've done already. I mentioned to you the 80s were good. I think the good times, I was in my 20s, so it's a bit biased. But we need to bring back the concentration of CO2 in the atmosphere to lower level. We cannot be satisfied with a world at 1.5 degrees above pre-industrial. That's not good for the ice sheet. If you ask me, I'll say no. It's already a point where we destabilize parts of the ice. So if we bring back colder conditions, the best we can do is slow it down to a stop. But we won't go back to where it was initially. It's too late for that. The 1.5 degree Paris Accord, that's good. Politicians came up with the 1.5 degrees. So now there's a new report showing 2 degrees would be much worse than 1.5 degree. But that doesn't mean that 1.5 degrees is an acceptable solution. We will have to share the technology with other countries. It's a global problem. If California does great, if the US does great, that's all right. Europe, China, but we have to include everybody, and some people don't have the technology, so we're going to have to share that. Now, I'm a little bit tired, of course, to be the bearer of bad news, but I have to say it as it is. Right? There's no reason to hide the truth, because the data, I've been looking at this data for 30 years, and it's a little bit overwhelming, the magnitude of the changes. It goes beyond what anyone was projecting. Even the most crazy scientists did not project something like this. But the solutions are very positive. I think it's very important to emphasize that. I don't want children to feel like it's doomsday and we're all screwed, because that's not true. The solutions can be implemented in a good way. It can be fun, create jobs. Right? We're not going to suffer. We're not going to have to tighten our belt. We're not going to have to pay the price to do that. Quite the opposite. Right? And at the end of the day, we're talking about a world informed by science. That's the key, and that's why the role of an educational institution is so important in this, to promote clean energy, clean air, clean water, sustainable development, environmental justice, and who doesn't want that? Right? Thank you very much.